Hello all. I want to talk to you today about atomic orbitals. What exactly is an atomic orbital? I want to talk to you about the quantum numbers that describe atomic orbitals. I also want to talk to you about nodes. So nodes are regions within an atomic orbital. I want to talk to you about nodes. I want to show you how to determine the total number of nodes in an atomic orbital given that orbital's quantum number designation. And I also want to show you how to differentiate between the two different types of nodes that are present in atomic orbitals. So let's go ahead and get straight into it, and let's talk about some of the basics that we need to get out of the way anytime we're talking about atomic orbitals. First of all, we have these three different quantum numbers that describe atomic orbitals. We have the principal quantum number n, we have the orbital angular momentum quantum number, and this is a L, a lowercase l, and it's usually shown as an italic. And then lastly, the third quantum number that we have to describe an atomic orbital is the magnetic quantum number m sub l. Okay, so let's talk about them one at a time. The first quantum number that you need to be familiar with is the principal quantum number, and this denotes the principal energy level of an atomic orbital. This was the first quantum number to be used to describe the region of space an electron would be found about its given nucleus. Now, this quantum number shows up in the Bohr model of the hydrogen atom. And we know that for one electron atoms, this is the only quantum number really that is important to describe the overall energy of an electron in an orbital. Now, n can take any positive integer value, including 0, up to infinity. And as n increases, the principal energy level for the orbital increases as well. Okay. Now, when n equals infinity, that would indicate that the electron in a given orbital would be completely removed or ionized and dissociated completely from the respective nucleus. Okay, so we can typically think about n as indicating the size of an orbital. So as an orbital increases in energy, um, the probability of the electron uh, being close to the nucleus decreases, and the orbital basically grows in size. So simply as n increases, the orbital size increases as well. So that's a very it's a very simple association you want to be able to make. Now the second quantum number that we have to describe orbitals is the orbital angular momentum number, this italic L, and it denotes the sublevel of an orbital. So orbitals are found in principal energy levels, and then within their given principal energy level, they're found within a sublevel, and the sublevels are denoted as S, P, D, and F. And each of these sublevels has a integer orbital angular momentum number assigned to it. So an S sublevel has an orbital angular momentum number of 0. P is 1, a D is 2, and an F is 3. Okay, so each of these sublevels has their own integer orbital angular momentum number. And in terms of energy, well, we know that as n increases, the energy of the orbital also increases. Well, when we go from S to P to D to F, the orbitals also increase in energy within a principal energy level. So for example, in the second principal energy level, it's the energy level that we talk about a lot. Within the second principal energy level, the P sublevel is higher in energy than the S sublevel, and the D sublevel is higher in energy than the P sublevel, and the F is higher in energy than the D sublevel. Okay, so therefore a 2s orbital, so a 2s orbital is found within the second principal energy level. Okay, that's what the 2 means. In a 2s orbital, okay, it's going to be lower in energy than a 2d 2d orbital. Okay, now lastly we have the magnetic quantum number m sub l, and this number specifies the orientation of the orbital motion of an electron. Simplistically, this is what's commonly said. It describes the orbital shape and also indicates its orientation in space. Okay, so this number takes on integer values, okay, but it's bound by its orbital angular momentum number. Okay, so m sub l, the magnetic quantum number, can take any integer value between negative L, greater than or equal to negative L, less than or equal to positive L. Okay, so for example, if we are talking about orbitals within the D sublevel, well, D has an orbital angular momentum number of 2, so therefore m sub l can have 5 possible values: -2, -1, 0, 1, and 2. Okay, so just very clearly, in any D sublevel, there are 5 orbitals total. Each of these D orbitals has a different m sub l. Okay, so just to be totally clear, when we are speaking about an F sublevel, well, we notice that the orbital angular momentum number for an F sublevel is 3, so therefore the possible m sub l values within an F sublevel are going to be -3, -2, -1, 0, 1, 2, and 3. Notice that that's 7 integer values. Each of those integer values describes a different orbital. Okay, so in any F sublevel, there's going to be 7 different, and we're going to say degenerate orbitals. Those orbitals have the same energies. Okay, so that's the term we use. We use the term degenerate when we're talking about orbital energies that are identical. Now, we can talk about orbital nodes, and this is an important concept when we are talking about atomic orbitals. Atomic orbitals are really regions of space that contain a high probability of containing an electron of a given energy. Okay, so they're really volumes of space, and they're often represented as boundary surfaces, which enclose most of the space wherein an electron in a given orbital would be found. Now, nodes are regions within an orbital where the probability of finding an electron equals 0. So within the region of space where the electron is probably found, given an energy, we have these intersecting planes and cones referred to as nodes. Okay, and we're going to see that visually in just a minute when we use Orbital Viewer coming up here. Now check this out. For a given orbital, the total number of nodes is n minus 1. So if we are in a sublevel that's within the principal quantum level 4, n equals 4, well, then we're going to know that each of those orbitals, okay, is going to have 3 nodes within. So 4 minus 1 is 3. So for example, a 4d orbital is going to have 3 nodes. A 4f orbital is going to have 3 nodes. A 4s orbital is going to have 3 nodes. Okay, that's just total nodes in the orbital. Principal quantum number minus 1. Now, there's two different types of nodes that can be present in atomic orbitals. We have angular nodes and we have radial nodes. Angular nodes are often referred to as nodal planes or planar nodes. Now, some angular nodes are like two-dimensional planes, but there's also angular nodes that are like cone-shaped. So I tend to refer to angular nodes simply as angular nodes rather than nodal planes. For the most part, but do be aware that language is used. Also, the other kind of node that we can find are radial nodes. Okay. Now, notice that angular nodes are defined by the orbital angular momentum number. Okay. So notice that when L is equal to 0, which it is for an S sublevel, when L is equal to 0, we're going to find 0 angular nodes present. Okay. And then radial nodes, they make up the difference between total nodes in an orbital and the number of angular nodes. So here we have a nice summary example. A 3p orbital has n equals 3. Okay, so again, that principal energy level is denoted by the coefficient 3 in front of the letter p. Okay, it has a angular momentum quantum number of 1. Now that's determined by the letter p, right? So remember that the p sublevel has an angular momentum number of 1. All right. And we can have m sub l, check it out. So when L is equal to 1, m sub L can be equal to negative 1, 0, and also 1, right? Okay. We can have m sub L of 1, 0, sorry, negative 1, 0, and plus 1. The negative sign is up here. Negative 1, 0, and plus 1. Note that there are 3 different p orbitals in the p sublevel of any principal energy level. That is, that if that energy level has a p sublevel, note that the n equals 1 principal energy level has no p sublevel. In the first principal energy level, there's only one sublevel present, and it's the S sublevel. When we get into the second principal energy level, that's when we have an S sublevel and a p sublevel. And when we get into the third principal energy level, that's where we finally have an S sublevel, a p sublevel, and a d sublevel. So basically it goes like that. Okay, so in the first principal energy level, only S, and then when we go to the second principal energy level, then we get S and P. Okay, and they continue increasing in that way. Notice that each one of these m sub L values corresponds to a different orbital. So that's something that I mentioned earlier, but let me just remind you of that. Okay. So each of these orbitals actually are going to be orthogonal to each other. Okay, so let's go ahead and look at Orbital Viewer by David Manthey. So this program was developed by David Manthey, and you can go ahead and email him here if you like, and you can visit this URL to download this program and use it on your own. I think it only really works well on PCs, but I'm sure you can get it to work well on a Mac somehow. I'm not quite sure, but it's an older program, right? You can see that the copyright is 97 to 2004. So I don't think it was developed for use on Apple products at that time. But feel free to give it a go. This is a very useful program. We can use this program to visualize atomic orbitals. Now, I didn't mention this earlier, but I'm going to mention it now. These atomic orbitals are actually defined by mathematical functions, wave functions. And these wave functions contain these quantum numbers n, l, and m sub l. And by varying these quantum numbers, we vary the orbital itself. So let's go ahead and let's use David Manthey's program to look at how variations in these quantum numbers can affect our resulting atomic orbital. So I've already opened the program and I've changed from the default orbital to a s orbital. So let's start over. So when you open the program and you go to File New, this is the first orbital that's shown to you. It's a 4f atomic orbital. Okay. Now it's pretty weird looking, right? It looks nothing like the Bohr orbits, in my opinion. You know, obviously there is still some carryover, but it looks quite different than an orbit, right? It's really just representing a three-dimensional volume of space where the electron has a high probability of being found if it has the 4f orbital energy. So we're just looking at one atom right now. We're in the fourth principal energy level. We're in the F sublevel. That is L is equal to 3. And we are looking at the orbital with the M sub L magnetic quantum number of 0. We're looking at the hydrogen atom as well. Okay. So I want to demonstrate this. Look what happens when we change the protons from 1 all the way up to 6. Let's see what happens. Look at how much smaller that got. That's because the effective pull on the electron in the orbital has been increased by an increased nuclear charge. Let's go ahead and just leave this as hydrogen for now. And let's go ahead. Let's see, it's going to get bigger, right? Okay, let's go ahead and look at the simplest, lowest energy of all atomic orbitals. What is the M sub L values that can be assigned? What are the M sub L values that can be assigned when we are in the S sublevel, when our angular momentum quantum number is 0? Only 0, right? So check this out. This is just a sphere. So this is much more similar to the Bohr orbits concept than I think what we just looked at with the 4f atomic orbital. So here we go. The lowest energy orbital of all is the 1s. Now again, we're in the first principal energy level. It doesn't get any lower than that. There's no 0 principal energy level. And we are in the lowest energy sublevel for any principal energy level. Now remember that in the first principal energy level we only have that S sublevel, none of the other sublevels as well. Okay, how many nodes should we have in this orbital? Well, we know that total nodes is n minus 1, n is 1, 1 minus 1 is 0. We shouldn't have any nodes, and that's why we just get this uninterrupted sphere. Let's go ahead and go up to the second highest energy orbital. Let's look at the 2s orbital. So notice that while it was developing, you saw that orange sphere inside, and now you see the blue sphere on the outside. Let's go ahead and insert a plane. Cut away, let's do it 0, 0, 0 and see how that works out for us. Check this out. It works pretty well, huh? We have this orange sphere and this blue sphere. What's up with that? Okay, well, remember that these orbitals come from wave functions. Whenever the wave function changes from positive to negative value, you have an intersection of the x-axis. That's a change of sign in the wave function. Whenever there's a change of sign of the wave function, you end up with a node. Okay? So there was a change in the size of the wave function between this orange region and this blue region right here. Okay? And remember that angular nodes is given by L. Well, L is equal to 0 for an S sublevel. So therefore, we have one radial node. Okay, and the radial node has the same shape as the sphere. Let me see if we can do this. If we can insert something else. Let's see what happens if we do. Let's see what happens if we do. Well, we'll try this corner. So hopefully you can see that orange region is in fact spherical. The blue region is also spherical. So there's like a sphere node separating them. And again, we're not looking at the whole orbital right now. We're not looking at the whole 2s orbital because we're cutting part of it away just so we can inspect the radial node that's found within the orbital. Let's look at the next higher energy orbitals, the 2p orbitals. Notice that with the angular momentum quantum number being 1, we have now 3 m sub L values available to us, each representing a different orbital within the second principal energy level. We have -1, 0, and 1. So let's go ahead and look at -1. And I'm going to go ahead and I'll remove that that corner so we can see the entire orbital. Okay, so we basically have like two lobes. So the p orbitals are often described as being dumbbell shaped. You know, I go to the gym quite a bit and I don't quite see that. But I mean, obviously there is some similarity, right? But where would you put your hand? Really, there's no area for that, right? So you basically get like a dumbbell. We can say that. Okay. Now notice that we again are in the second principal energy level. Therefore, we should have a node, right? Total number of nodes, in this case, 2 minus 1, that's 1. We should have one node. Our angular momentum quantum number is 1, so therefore we should have one angular node, and 1 minus 1 is 0, therefore we should have 0 radial nodes. So we don't see a radial node here. What we do see is this like plane of separation between the two sides of the orbital. And this is actually a nodal plane. Okay, and that's why a lot of times these angular nodes are referred to as nodal planes, because some angular nodes are actually nodal planes. So the angular node cuts right through the region of the nucleus and it removes spaces close to the nucleus. So you basically get an electron at higher and higher energies as angular nodes are added in, because the lowest energy space an electron can be is close to the nucleus. The further it gets away from the nucleus, the higher in energy it gets. Okay, and that's really why like a 4f orbital is higher in energy than a 4s. Okay, it's just because for the f orbitals we have regions close to the nucleus that have been removed by these angular nodes. So angular nodes are always cutting spaces away near the nucleus. Let's look at let's just change this really quick and see. Let's just change in sub L and see what happens. Okay, notice that we have the exact same shape, but the orientation in space has changed. Let's go to m sub L is equal to 1. So again, same shape, but just orientation in space. So the p orbitals are actually orthogonal to each other. So each one goes along an axis x, y, and z. And let's go back to let's just start again at the very beginning so we can reset our spatial orientation. And let's look at a 3D orbital. Let's see how this looks. Okay, 3D. Let's think about the nodes. Okay, so how many total nodes? 3 minus 1 is 2. Okay, L is equal to 2, so therefore there should be 2 angular nodes. And by default, again, 2 minus 2 is 0, should be 0 radial nodes. And that's what we see. Now for each of these orbitals that we generate, okay, the nucleus is right in the middle of the of the of the screen. Okay, so the nucleus is right in here. Okay, so we see different colors indicating sign change 2 times in the origin wave function. Okay, but what exactly are we looking at? Well, we're not looking at planes. Okay, we're looking at these like cones that cut in towards the nucleus right in here. Okay, it's kind of like cones cutting in on both sides. So those are our angular nodes in this orbital. Okay, so hopefully this gives you some insight into atomic orbitals, what exactly they are, how the quantum numbers affect the size and shape and orientation of orbitals. And just let me know if you have any questions, and good luck with your atomic orbital studies and chemistry understanding in general.